I've known actually for quite a while. He took a class with me, then I was on the master's thesis committee, where he was working with Professor Melise, and then he changed topics and advisors, and he's been working with Jennifer PD for the last couple of years maybe, right? And I don't know what he's been working on, so I'm really looking forward to finding out.
So, good afternoon, everyone. Today I'm going to talk about my talk on clustering and ranking heterogeneous information network by a Gamma-Poisson model. Probably the title does not make sense to most of the audience, but basically that is a data mining problem, which means we try to find some patterns or discover some knowledge from a typically pretty large database. And in this particular project, we are trying to deal with a particular type of data, which means it's information network data. So basically, for information network, it means it is a graphical representation for the objects and the interaction between the objects. For example, in this network, usually the objects are represented using the vertices, and the relationships or the interactions between the objects are represented using edges between the vertices. A typical example might be a social network or friendship network, where the objects are the people in the community, and the connections or the edges in the network are in the friendship relationship between the people. And there are other examples for the information network. For example, a gene regulatory network, which involves two types of objects. That is the transcription factor sample 10, and it involves several different types of relationships between the two different types of objects, including the promoter binding, expression, regulation, and so on. It has multiple types of relationships between multiple types of objects. And the other example might be a bibliography network, which involves three different types of objects. That is the author, the word, and the conferences. And it involves four different types of relationships between these objects, including two of the author might co-author a certain paper. An author might use a certain word in his paper. An author publishes at certain conferences, and the word appears in a certain conferences. So it will involve three different types of objects and four different types of relationships in a single network data. So because of the actually different types of data can be represented using the information network, therefore the analysis for the information network has drawn plenty attention from different academic fields. And in general, the network can be divided into two different types. That is the homogeneous and heterogeneous ones. For homogeneous network, it means it involves only one type of object and one type of edges. For example, the social network, which involves only one type of object, that is the people, and one type of relationships, that is the friendship between the people. However, usually we need to deal with more complex relationships in certain analyses. For example, in the gene regulatory network and bibliography network, it involves multiple types of objects and multiple types of edges between the objects. In this talk, we will focus on the undirected heterogeneous information network, which means, first of all, it's undirected. Actually, for the gene regulatory network, the relationship is directed, so we do not consider that problem. We focus on a network similar to bibliography network, which is an undirected network and involves multiple types of objects and multiple types of relationship between the objects. For information network analysis, the most frequently applied techniques involves clustering and ranking. For clustering, the task is to try to divide the objects into several groups, such that within each of the groups, the objects are well connected with each other, while between different groups, the objects are less connected with each other. For example, in this social network, actually it is clustered, and it is divided into several clusters, which is represented by different colors. And we can observe that, for example, for vertices in red, they are more connected with each other, but there are less connections between the vertices in red and the vertices in green. So it is sort of a cluster structure in this information network. Another problem usually we want to solve is the ranking problem. We want to identify the more important objects from the less important object in the network. And one of the most famous algorithm for this is the PageRank, which the size of the smiling face actually is given by all of the total size of the smiling face. They are pointing to the face. For example, for the largest yellow smiling faces, there are several medium and smaller objects. They are pointing to this face, therefore, which makes this face is the largest and most important in the network. Usually, clustering and ranking are treated as independent and separate tasks that are not interact with each other. But actually, in some of the tasks, it might be a good idea to combine clustering and ranking together. For example, in the bibliography network, if we directly rank the authors just according to the importance, the result might not make sense because the authors might come from different academic fields. And because the difference in different academic fields, such as the publication difficulty is different. Therefore, the comparison might not directly make sense. So basically, we want to combine the clustering and ranking together, which means we divide those authors into different academic fields and give the ranking in each of the academic fields separately, which might give a better representation for the data and gives a better analysis for the data. Therefore, in this talk, I will talk about a model which tries to simultaneously achieve clustering and ranking in a heterogeneous information network. Our approach is a probabilistic generative model approach, which means we assume that the observation or the information network is given by a certain random process that are parameterized by several latent variables. And we try to learn those latent variables after observing a certain observation or a certain information network. So here is the assumption of our model. We assume that there is a ranking scores that represents the importance of the object in each of the clusters. For example, if we assume there are n different objects and k different clusters, then we can form n by k ranking score matrix. In the matrix, we can get both the clustering and ranking results because in the matrix, we assume that if a vertex belongs to a certain cluster, then the importance of that object in that cluster should be higher than the importance in the other clusters. Therefore, we can get the clustering results by simply compare the values in each row of the matrix. Similarly, if we want to compare two of the vertices in different clusters, we simply compare the column in this similarity matrix. If one object is more important than the other one, that means the ranking score in that cluster is going to be higher than the other object. And that is the basic assumption behind our model. As a generative model, we assume that the scores actually comes from a certain distribution. Here we choose to be a gamma distribution because we assume that the ranking scores are positive real numbers. Here is some sample PDF for the gamma distribution. We choose gamma distribution because it will be more convenient for us to get a posterior distribution or in the inference stage. Another thing we want to model in a heterogeneous information network is the intensity of the edge type. Because some of the edge types might tend to have more connections than the other edge types. For example, in a bibliography networks, there might be more connections between the authors to the conferences because there are simply less conferences than the authors, so the connection might be more tense. However, in the, for example, in the connection between the authors and the words, because both there are large amounts of words and large amounts of authors, the connection is going to be sparse. So we need to model this phenomenon. And here we just choose another parameter which is called lambda to parameterize those intensity of different edge type. We also assume that this lambda comes from a gamma distribution, which gives a positive real number to model the phenomenon. So as a generative model, we want to generate the whole network according to the Latin variables introduced behind. Here we assume that the connections are given by the Poisson distribution, which are parameterized by both the intensity of the edge type and the dot product of the ranking scores. The reason why we choose this parameter will be introduced in next slide. And here is some samples for the Poisson distribution, which is parameterized by a single parameter lambda, which gives both the mean and the variance of the distribution. So why we choose the dot product in this parameter? The reason is that actually a dot product can be factorized into 3 parts. The first is the cosine theta, which is sort of a similarity measure between 2 of the vectors. Because when the theta equal to 0, it means 2 of the vectors are parallel with each other, which means 2 of the vectors might come from the same clusters. And because we let the vector to be all positive, so the theta cannot be larger than 90 degrees. When it equals to 90 degrees, that means 2 of the vectors are orthogonal with each other, which means 2 of the vertices, 2 of the vectors are dissimilar with each other, and they might come from different clusters. Therefore, by considering this, in order to have large connections between 2 arbitrary points in the network, then 3 conditions need to be satisfied. The first is we need to have a large lambda, which means the intensity of the edge type needs to be high, which means with this edge type, we simply tend to have more connections than the other edge types. The second is it needs to have large cosine theta. As mentioned before, cosine theta is measured for the similarity, and here that means it needs to come from the same clusters. And the third condition is that it needs to have a large norm for each of the vectors. This means both vectors need to be, or both vertices need to be important in this network. By considering all of these 3 factors, actually we simultaneously consider the intensity of the edge type, the clustering results, and the ranking results simultaneously. And that is the motivation of our model. So here is the summary of the model. First of all, we generate some Latin variables that are the ranking scores and the intensity of edge type. And then the network is generated using these random Latin variables using a Poisson distribution. So the task is we need to try to find the optimal Latin variables that can fit the observed network or the observations. So that means we need to evaluate the posterior distribution for the Latin variables given the observation or the heterogeneous information network. It is computationally intractable to directly evaluate the posterior distribution because actually the model is quite complex. So we try to approximate the distributions using a method called mean field variational inference. And because it is not straightforward to directly comparing 2 vectors because they are actually random variables, the value is not fixed, so it's not straightforward to directly comparing those variables. So in these tasks, actually we try to compare the expected values of those Latin variables rather than the true value of the random variables. So example, we test our model on two different real data, which is the DBLP dataset and ELP dataset. We also compare our method with different state-of-the-art method. As mentioned before, the DBLP dataset is a bibliography dataset which involves the author, the words, and conferences, and involves different relationships between those objects. And this dataset actually involved the conferences from different academic fields, including the database, data mining, machine learning, and information retrieval. And we try to apply our model on this dataset. First of all, we consider the classification accuracy for those datasets. We find that our method actually can outperform the state-of-the-art method. And here we can see the ranking results for each of the clusters using our model. For example, in the field of database, we find that the top 3 words in this field are data, database, and databases. Basically, that is the most frequently applied words in this academic field. Basically, that means our method can recover the top words that are used in each of the academic fields. And similarly, we find that we can find the top conferences according to the number of publications in each of the academic fields. So we also apply it to another data set, that is ELP data set, which involves the reviews given by a certain user to a certain businesses, and each of the review contains a certain word. We test our method on 3 different tasks with the same data set, and we also observe that actually our method can outperform most of the state-of-the-art method. So basically, this is the conclusion of the presentation. First of all, I try to introduce the problem of the related to the information network analysis. And I introduce a generative model that tries to solve the clustering and ranking problem for the information network. In this model, I introduce the concept of ranking scores that conveys both clustering and ranking information. And the ranking scores we assume comes from a gamma distribution, while the number of edges comes from a Poisson distribution. And I have demonstrated the results of the model on 2 real data sets, that is the DBLP and ELP data set. So that's the end of my presentation. I would like to answer any questions.
Hi. So you've demonstrated this with 2 realistic data sets. Have you gone to the developers of the Yelp site and talked to them about the results that you've obtained and gotten feedback as to whether they would be interested in working with your group or not?
No, actually, in the ELP data set, there are it can be divided into several categories. The business can be divided into several categories, and it's already given in the data set. So we just try to recover the category which is already known. So it might not be, very interesting.
You started to answer it, but I was going to ask, could you describe what the tasks are, like what you were classifying in each of the data sets? What your goal was in each of the, for the experiments?
We just try to classify all of the objects in the network.
So that was data that was
So
in the
that
data
means-
set?
Sorry?
So you just held out a part of the data and used that as labels?
To
verify?
I use all, because all,
So I think I had the same, so what was the data you started with? And what was the goal? I think that the example, the Yelp example in particular, was just not clear to me either.
Yeah.
And I think that probably prompted Michael's question as well. So what was the data you started with here?
for example, in this data, that means there are several reviews. which contains several words, is a sentence or a paragraph.
Okay,
And then those reviews are given by a certain users to a certain businesses.
okay,
So we try to cluster all of these objects, like we can try to cluster those business reviews words and users into several groups. And because in some groups, for example, some words are more frequently used to describe a certain category data. So we can try to recover those structure, like which words are most frequently used in one of the categories.
so you tried to figure out which reviews were for restaurants and which
Yeah.
reviews were for shopping,
And
and what's level one?
level one is several categories, like I cannot remember, like I think it includes restaurants, shoppings, and something like that. It includes several different categories.
Okay, so the idea was to figure out what type of business it was by cluster, and which businesses were,
Yeah,
what's the ranking here?
I don't give the ranking result because it's quite
just a
noisy,
clustering.
actually.
It's just a clustering problem.
Yeah.
So the idea is to figure out which type of business it was by looking at the users, the words in their review. We use, that's the data, it's the users, the name of the user, or the handle of the user, and the words in the review.
Actually, only the businesses has the label, so I can only validate those results on the businesses. We don't have the labels for the users or the reviews.
So you're trying to take the reviews and cluster them so that you can label which reviews are for what type of business?
Yeah, and we simultaneously also cluster the businesses into several clusters. We know which business belongs to which clusters too.
But you didn't use that information in training, you just
No,
used that for
I-
test,
It's just for
for
validating.
validating. And what was the task in the other data set?
It's similar data set. That means we know that a certain authors has some co-author with other authors and in a certain paper. And in one of the papers, the author would use a certain word, and an author might publish his papers or her papers on a certain conferences. And certain words might appear in certain conferences.
Right, I get the part of the model, but how are you classifying, what, you got 100% accuracy at what task?
This is on the conferences task.
So that we're covering the conference
Yeah, into the right clusters.
into certain clusters that were predefined.
Yeah.
And so
We
what
know
was,
there are only 4 clusters.
so what was the data here? The data was just the papers themselves?
It's not the paper itself, but the connections due to the paper. For example, 2 of the authors co-author a certain number of
But
papers.
the
So,
conference was not part of, conference label was not part of the data. Okay.
we have the labels, but in training we do not use the labels in the training process. It's a unsupervised learning process, which means we won't use the labels in the training part, but we use it as a validation for the results.
But you know which papers were in the same
Yeah,
conference?
we know,
Which papers were in the same conference, you don't know which conference it was, is that the idea?
actually we know which author has published which paper on which
In
conference.
the same conference, you know which authors published in the same conference?
Yeah,
Okay.
but we don't know, the classification for the conferences,
Yeah.
and then it will be the task for the training.
So the task was to define what type of conference each paper belongs to?
Yes, so try to divide the conferences into several clusters, and we can also divide those authors and words into several clusters in this.
And so what's an accurate classification of the author?
So
What are you trying to recover about the author that you judge accuracy based on?
we have the labels for the authors, like we know which authors belong to which academic fields.
I see, so you try
So
to
we-
classify the authors into one of those 4 fields.
Yeah, and try to compare.
And
the-
can authors be in more than one of those 4 fields, or it's a,
Currently, we assume we know the number of the fields in this model. We know that we need to recover 4 of the academic fields. So that is a parameter for the model.
and can authors be in more than one field, or just all in one field?
It could be sort of more than one field, but I just classify those authors to the most influential
Yeah, okay.
field,
Yep.
but it might have influenced them in more than one field.
What top 5 words? What algorithm did you use to extract top 5 words? Like words, database and databases? Is there any difference between these kind of words?
Sorry, could you?
What algorithm did you use to extract top 5 words?
It just try to comparing the scores and
That's
Did
what
like
his model
TF-IDF
learns.
or?
No, it's how his model is clustering.
Oh.
It's clustering and ranking, so
And
there's a-
ranking.
so the
But-
ranking would give you the, right? You're both clustering and
Yeah,
ranking
yeah,
simultaneously,
yeah.
so you're extracting the ranks here for the 5 words. Anybody else? Any questions? Okay, thank the speaker again.